Right. So the Simscape block for the PMBDC motor has two parts, electrical and mechanical. And the mechanical side of the block will handle will impart a torque on the inertia, and the positive direction of that torque would be from C to R. Now the effect of gravity is also a torque as well, and this will create the signal, and the C and R ports of the ideal torque source upon receiving the signal will impart the torque in a positive direction of C to R, and the torques of the motor and torques of the gravity needs to be combined. So once again, following the C and R, connecting all the C's and connecting all the R together works fine as well, and I'll explain later why this works in this particular case. Right now, let's just refer to the rule of thumb of connecting all these together. In essence, because I have connected the C's and R's together, these two torque sources now are connected in parallel. Just keep that in mind. And the signal from the Simulink block set for the gravity cannot be converted here, since these are two kinds of signals. Converters are needed to make the connections. And that's done. Now everything's fine with regards to the mechanical side, and we need to finish the electrical side of the motor, and our model would be good to go. So there are two terminals in this block, the positive and negative. We can either connect a constant voltage power supply, or we can connect it through motor controllers and PWM generators. We could add an H bridge over here and a PWM source prior to the H bridge and some signal to generate a PWM duty cycle, and connect these together and impart some sort of controlled voltage to the DC motor. That's possible, but at the moment we'll steer clear of that and do what's necessary and to model what we have been discussing since lecture 2, that is simply connecting a constant voltage and predicting what would happen. The voltage can be modeled using a block called constant voltage source. Right. So the name is just voltage, and upon double clicking it, it will bring up the dialog box for the block, and the same block can be used to impart a DC and AC voltage or a combination of those two. And in this case we won't be needing the AC component, so setting the AC magnitude to 0 essentially cancel out any AC components. We'll specify the DC magnitude to 12, since that's the voltage we have been dealing with since our first lecture. And we are forgetting something over here. Just like in the mechanical side, we need the reference. So that's kind of like a cardinal rule with Simscape. We need an electrical reference. So electrical references are available from the foundational library and from the electrical block set as well. I'll choose the second option, since I advise you to do so during the physical lecture, but I have found out that whether you whatever choice you choose, it doesn't really matter, right? So that's done. References are done, and there's some other thing that I quite forgot to do, and that's the insertion of a negative sign prior to connecting the two torques together. If you remember this model, the mechatronics model that we were studying, we define the problem in a manner that the DC motor will be wired, which will impart a counterclockwise torque, and based on the starting position of our rod, the gravity was imparting a clockwise torque. So the directions are opposites, and so if the counterclockwise direction is taken as positive, then any clockwise torque needs to be negated prior to making the addition. So that can be done by introduction of a gain block with the gain set to -1. And I think I forgot to include the effect, the -1 in the physical lecture as well. So apologies for that. And that kind of completes our model. I hope. I'm wrong again. I am yet to parameterize the PMBDC motor, and let's do that as well. So I double clicked it, brought up the motor. The field type is permanent magnet, since the motor we are using has a permanent magnet for the field. There are three options for model parameterization as we discussed last week, and here comes quite the tricky part. Since I am the 775 Pro motor that we have been discussing so far is kind of a hobbyist motor, and PDF datasheets, the datasheets available for the 775 motor aren't quite comprehensive, like many of the motors you see from reputed manufacturers. So based on the limited amount of characteristic parameters that they have provided, we must select the parameterization approach. So if we were to use the parameterization approach of specifying equivalent circuit parameters, we would needing armature resistance, inductance, back EMF constants, and so on. None of which are specified over here, so this is definitely not going to work. We'll take a look at rated load and speed. So armature inductance is once again not specified. No load speed can be figured out from the curve. No load speed means the RPM or whatever, the angular speed that when the torque output is 0. Essentially the RPM or the angular speed at this point. Rated speed can also be found, which is the maximum speed you'll obtain at any given voltage. Rated load is also visible, and as is rated DC supply voltage, which is 12, since the motor hasn't provided any. Yeah, I think in another version of this datasheet I found that it's rated at 12 volts. So let's just keep that in mind. So approach 3 is possible as well. Armature inductance is not provided. Let's check out approach 2. Once again, it requires armature inductance as well. Stall torque, no load speed, and rated DC voltage supply are quite readily available, quite directly available. So I think approach 2 would be more suitable, but you may be able to work out approach 3 as well. But 2 would be easier. So let's stick with 2. Leave armature inductance as is for now. So stall torque would be 0.7 Newton meters. No load speed would be what's over here. So that's kind of. So they use the term free speed. So but based on what you observe in the curve, no load speed is it will be quite clear that no load speed is what they mean by free speed. So you can change the units, but keep it at RPMs and specify it to 18,700. Rated voltage will be 12. So we can specify the rotor damping parameters as well, and the rotor inertia too, but let's keep it at the default values of extremely small ones.